Geiger-Müller counter. In 1908, Geiger and Müller designed a highly sensitive scientific device to detect charged particles, which is a efficient nuclear detector principle. It is based upon the principle of ionization of gas. When a charged particle passes through a gas, ionizes it. The electrons so produced during ionization get accelerated under a high potential and produce further ionization. This ionization is called indirect ionization. A large number of electrons are produced which are collected by a positive electrode. Therefore, this counter is sensitive to even very low energy radiation. The important feature of this detector is that the size of the electric pulse generated is independent of the energy of incident particles. Construction. The GM tube consists of a cylindrical metallic envelope which acts as a cathode. This cylindrical tube is about 15 to 50 cm long. A thin tungsten wire of 0.5 mm diameter placed inside the hollow copper tube acts as anode. The positive terminal of high tension battery is connected to the tungsten wire through a high resistance R, and negative terminal is connected to the copper cylinder. A glass bead is used to cover the free end of the wire in the chamber. This bead is used to avoid corona discharge, which may build up at the sharp point. A thin mica window is provided at one end of the chamber so that alpha and beta particle may enter the chamber. In a GM counter, a cylindrical metal coating inside a glass envelope is also used in place of the metallic cylinder. Then the inner metal coating serves the purpose of cathode. The cathode surface is made of stainless steel or nickel or any other material having large value of work function. The GM tube is filled with an inert gas like argon, neon, helium, etc. The electric pulse produced is amplified using an amplifier and fed to a counter. Working. When a single charged particle enters the Geiger-Müller tube, ionization of gas takes place. Electrons produced get accelerated towards the central anode and strike the gas atoms, thus producing more electrons from the gas or air present inside the tube. These new electrons are also accelerated and may produce more ion pairs. As a result, an avalanche occurs and a very large number of electrons reaches the central anode and get collected by it. In this way, the initial formation of a single ion pair results in a very large pulse of current to the anode, whose each particle passing through the tube is automatically counted. A resistor R is connected in the Geiger counter circuit as shown in figure. The current pulse I flowing through it produces a voltage pulse V, which can be amplified by an electronic amplifier and counted by an electronic counter. It might be expected that if an ionizing particle initially produces trail of ion pairs in the gas, the resulting current pulse will be larger than the originating from a single ion pair. For moderate value of the potential difference between anode and the cathode, this found to be the case. However, as this potential difference is increased, this variation in the size of current pulse gradually disappears. Ultimately, it is found that the size of current pulse becomes effectively independent of the initial density of ionization for quite a range of potential differences. The counter then gives a full avalanche of nearly constant size for any particle counted. In this region, it is said to operate on the Platway or in the Geiger region. This is the normal mode of operation since the counter sensitivity is highest and the counting efficiency is independent of tube voltage over a reasonable range, so that the supply voltage is not critical. A counter operated in this fashion cannot give any information about the type of particle producing the count or its energy. The first counter of this type was constructed by Geiger and Müller in 1928, and these devices are now most commonly known as Geiger counters.